aim is now to install the turbine above tail race level. But when we install the turbine above tail race level, so our available head, whatever gross head available with us, that is reduced by an amount by which we install the turbine above tail race level. So that amount of head goes waste. That is not used in a useful work. So that is the disadvantage of this by installing the turbine above tail race level. Okay. Now this limitation is removed, you can say, by the use of draft tube. How? Now you can see, now we have three main functions for a draft tube. The first function is it will prevent accident and splashing of water. So at the outlet you can see when we install a turbine above tail race level, so there is the splashing of water, maybe some accident takes place. To avoid that, we use a draft tube at the outlet of the turbine and we dip that draft tube into the tail race. Okay. The second function is the turbine can be installed above tail race level without reducing the working head. Now this one is the important function of draft tube. This is how we can remove this deficiency of installing a turbine above tail race level. So this is the important function of draft tube that we discuss in detail next. Then the third function, the working head okay, or you can say the energy transfer in the turbine can still be increased to some extent by adopting a draft tube of enlarging cross section or increasing cross section. Okay, so you can say in third function, the working head or energy transfer can further be increased by using a draft tube of increasing cross section, or you can say by using a draft tube of enlarging cross section. So these are the three main functions of draft tube. Now the last function you can see, if I have a draft tube of uniform cross section, that is something like this, and I have a draft tube of enlarging cross section, that is like this. Okay, so here the leaving velocity is VO. If we neglect the friction in the draft tube, the leaving velocity from the draft tube is VO. So that is my, you can say my energy that goes waste as VO square by 2 per unit mass. Okay. Now in this case of enlarging cross section, here if velocity is VO, so here the velocity is VD, and this VD is always less than VO. So in this case, in second case, my wastage energy is as VD square by 2. This is again per unit mass. Okay. So this wastage of energy is less as compared to VO square by 2, that is in case 1. This is for case 1 and this is for case 2. Okay, so you can say the working head, that is the third function, the working head or energy transfer can be increased to some extent by using a draft tube of increasing cross section. That is the case 2. So here the wastage of energy per unit mass is with respect to VD square divided by 2. Okay, so this is the third function of draft tube. Now I talk about the second function now. Now for second function you have one diagram. Now you can see this diagram. So in this diagram I have the gross head as H. Okay, so this is, you can say this is the level of head race and this is the level of tail race. Okay, so here my working head is as H minus H dash. Okay, so here I install the turbine above tail race level at this height, that is H dash. So I mark here three sections. So section 1 at outlet of turbine, or you can say that is the inlet to the draft tube. Then my section 2, so this is my section 1, this is my section 2. So section 2 is at tail race level. And then my section 3 at exit of the draft tube. So these are my three sections over here. And here we have height H. So H is the length of the draft tube. Okay. So here I have two shapes of draft tube. One is of uniform cross section. You can see over here. Okay. So with this, the outlet velocity is VO. And then the second one is the velocity, the draft tube with increasing cross section, that is with these dotted line. Okay. Now here, when water comes out, the velocity is Vd. Okay, so Vd is less than Vo. Okay, so with this, I think the diagram is clear to you. Now I see the case 1. The case 1 is when I install the turbine at tail race level. That is my case 1. Now case 1 means when I install this turbine at section 2. So at that time you can see the energy change in the turbine. I write the energy change in the turbine. So the energy change is the energy supplied minus the leaving energy. Energy supplied minus the leaving energy. Okay, so this is equal to, now energy supplied when turbine is installed at tail race level, that is over here at section 2. So I have the available head is as H. So I can write this energy per unit mass, and that becomes GH. Okay, that becomes GH minus, now the leaving energy is with respect to VO, and that per unit mass I can write as VO square divided by 2. So this is per unit mass. Okay, or I can write this energy change in turbine per unit weight. So that is H minus VO square divided by 2G. This is per unit weight. So you can see here the energy transfer in the turbine when turbine is installed at the tail race level is equal to the available head minus the leaving energy per unit weight, that is VO square divided by 2G. Okay. Now this is the case when I have no draft tube. I have no draft tube. Now the second case you have turbine above tail race level, and again no draft tube, without draft tube. Now again I can write in that case energy transfer or energy change in the turbine, that is equal to the energy supplied minus the leaving energy. So now you can see here in this diagram the case When turbine is installed above the tail race level, that is over here in the diagram as shown, and we have no draft tube. So you can see here, now the available head is with respect to this height. So this height is equal to h minus h dash. So the energy supplied per unit mass, that I can write as g h minus h dash minus, now the leaving energy with respect to this velocity VO. So that is again per unit mass, VO square divided by 2. Okay, or per unit weight I can write it as h minus h dash minus VO square divided by 2g. So now you can see here the energy change in the turbine is reduced by an amount of h dash. Now this h dash is the height above which we install the turbine at the tail race level, or above the tail race level. Sorry. You can say this is the height above which we install the turbine from the tail race level. So that amount of head is going down in case turbine installed above the tail race level and there is no draft tube. Now the case 3 is, now turbine above tail race level with a draft tube of uniform cross section. Okay, so if we use a draft tube of uniform cross section, the velocity here you can see is VO. The same is at the outlet if we neglect the friction of the draft tube. So at the inlet to the draft tube at section 1 and at section 3, the velocity is same as VO. And the second thing is the pressure at the outlet of the turbine does not remain atmospheric. It becomes negative. It becomes less than atmospheric by an amount equal to the height of draft tube. Okay, by an amount equal to the height of the draft tube. So I repeat this. The pressure at the outlet of the turbine does not remain atmospheric. It becomes negative by an amount equal to the height of the draft tube. So now this thing I am going to prove. So for that, so first I write this thing at outlet of turbine, pressure is not atmospheric, and second thing is it becomes less than, or you can say it becomes negative by an amount equal to the height of the draft tube. Now this thing I have to prove now. So for that, now I am going to apply the Bernoulli's theorem at section 1 and 3. So when I apply the Bernoulli's theorem at section 1, you can see in this diagram. So at section 1, the pressure is PO, pressure intensity is PO. So I can write it as PO by rho plus VO square divided by 2 plus GH equal to, at section 3, that is my bottom line. So section 3 is here, that is my bottom line. So I can write it as P3 by rho plus 0 plus VO square by 2. Okay. Now I again apply Bernoulli's theorem at section 2 and 3. So section 2 is at tail race level. You can see here the section 2 is at tail race level and section 3 is at the outlet of the draft tube. So I can write here. So at section 2, the pressure is atmospheric, PA by rho plus GH minus H dash plus VO square divided by 2 equal to P3 by rho plus 0 plus VD square, VO square divided by 2. Okay. So from here I can find out P3 by rho. So P3 by rho, this comes out to be PA by rho plus, these two terms cancelled out, G H minus H dash. So I put this value of P3 by rho in my equation 1, put this value in equation 1. Okay, so I can write again PO by rho, this is equal to, now see on both sides, these two velocities cancels out. So I put here the value of P3 by rho, so that is PA by rho plus G H minus H dash, so minus this GH minus GH. So this gives me PO by rho is equal to PA by rho minus GH dash. So thus you can see the pressure at the outlet of the turbine becomes negative. You can see PO by rho. Okay. So PO by rho, that becomes less than atmospheric because you have negative sign over here, by an amount, this is less than atmospheric, by an amount equal to the height of the turbine above the tail race level. Okay, so that is my this point. That proves my second point. Okay, so now I write again the energy transfer. So that is equal to the energy at the inlet. So now the energy at the inlet, you can see in this diagram, turbine is above the tail race level with the draft tube of uniform cross section, that is again over here. So I can write it as G H minus H dash, okay, and the total energy at the outlet minus the total energy at the outlet is now VO square divided by 2. Now out of this energy, out of this waste energy, I extract amount equal to this one. Okay, so that is minus of GH dash. So this amount of energy I shifts to the energy that is transfer, and that is transferred to the useful work that I extract from the wastage energy or waste energy, you can say. Okay, so this I can write now. You can see, cancel the common terms. So this comes out to be GH minus VO square divided by 2. So this is again per unit mass. So now you can see this energy and see the energy in first case. Both are the same. Okay, so that proves my third function or second function of draft tube. That means the turbine can be installed above tail race level without reducing the working head. So here my working head is the energy transfer within the turbine, that is GH minus VO square divided by 2. Working head is GH. H you can say. So GH minus VO square divided by 2 is the amount of energy transfer per unit weight, per unit mass. So that is same as the case 1. So that proves my second function of draft tube. Okay. Then the fourth case I have turbine with a draft tube of enlarging section. So that is with dotted line. You can see with dotted line, these green dotted line. So at the inlet, I have velocity VO. At the outlet of the draft tube, I have velocity VD. Okay. So now you see how much pressure becomes less than atmospheric. So you can see here when I use apply the Bernoulli's equation at section 1 and section 3. You can see this relation. Okay, so here I have same VO square divided by 2. Now this term is replaced with VD square by 2. Okay, this is replaced by VD square by 2. Okay, also here the term is replaced by VD square by 2. So find out P3 by rho. Okay, and then find PO by rho. Now P3 by rho becomes You can see here P3 by rho is equal to PA by rho plus GH minus H dash. There is one more term plus VO square minus VD square divided by 2. Okay, so you can see use this P3 by rho in equation number 1. Find out PO by rho. So it is PA by rho plus GH minus H dash minus GH. Okay, there is one more term plus VO square minus VD square divided by 2. So PO by rho, PA by rho. Okay, write this term again with bracket. So GH dash here is plus VO square minus VD square divided by 2. Okay, so if I write this equation again, I can write it as PO by rho. This is PA by rho minus GH dash plus VO square minus VD square by 2 means this amount below atmospheric pressure. So PO by rho becomes less than atmospheric by an amount this much. Okay, then you see the energy transfer. So that energy transfer is equal to energy at inlet G H minus H dash minus the leaving energy VO square divided by 2. From this, the extracted part minus GH dash plus VO square minus VD square divided by 2. Okay, now you cancel out the common terms and this comes out to be GH minus VD square divided by 2. So obviously you can see the term VD square by 2 is less than VO square by 2. So that means this gap is the gap of energy transfer is more. Okay, so which shows that the energy transfer in the turbine has become further increased, has been further increased. So you can write here the energy transfer in the turbine has been further increased. Okay, so this is how we can use the draft tube. This all explains the functions of draft tube. Thank you.